Hi Year 10, this is our part 2 of resistance, and from this point onwards after this lesson we're just going to be showing the applications of all the things we've learnt so far about charge, current, voltage and resistance. So this kind of ties it all together, and before I get too far in I want a couple of big shout outs to some particular stars Year 10. My first one is Harry, who sat down and clearly had spent some time working all this out and first go 10 out of 10 on his quiz from last week. Not many other people could pull that off, but you know what, I was really pleased to see lots of people having a second go at the quiz and correcting the ones they got wrong. Now, that being said, there are some of you who are playing guess the answer, having a go, getting most of it wrong, then trying it again and seeing if you make some changes. Don't do it, guys. It stands out. I'm not interested in it, and I'd make these videos to help you so that when we come back to normality, you're not fighting from behind the 8 ball trying to catch up to where everybody else is. You have to take notes during the videos, you have to watch them all, and you have to have a go at the worked examples. Otherwise, you're going to really struggle going into year 11. So I need a little bit of independence stepping up here and a little bit of ownership. And if you dig in, and I did say there was a second shout out, and in fact, it's actually going to go to a whole class. 10-2A, you've impressed me no end. You have the highest percentage of students attempting the quiz for a second time round, which means you're showing great resilience. Anyway, enough of me talking. Let's get into resistance part 2. And as per usual, any questions, anything you get stuck on, email me and show me what you've tried. But in the meantime, make sure you're watching the video and pausing it, having go to the worked examples, and you'll find the quiz really, really easy, as long as you do this properly. Okay, so this will be your first one to hit the pause button on. Okay, so 2 questions, a pretty common one, true or false, and then a quick description one. So hit pause and I will go on to the answers. Okay, so the first one is if we add more resistors. Now, more resistors is one part of the problem, but we also need to know what kind of circuit it is. And if it's a series circuit, the answer is true. Well done if you got that one. Describe what happens to the total resistance if more resistors are added in. Now, again, more resistors, but what kind of circuit is it? Parallel. So the total resistance will go down. Okay, so if we're not getting a handle on that, so there's 2 types of circuits, and that determines what's happening to our resistance. so I love this word. We're going to master it, okay? Which means we're going to practice a lot more, guys. And if you don't practice, you won't get very good at it, and you'll struggle because these are easy marks to get if you know how to do it. So I'm going to keep showing you worked examples. You keep trying them, and I promise you, you will get good at it. So again, we're going to have a look at series and parallel circuits. The equation sheet, our equation sheet that you've all been making. And I have sent a message to all your parents, so if this is not on your revision notes, it's going to stand out to them. So please make sure you get on that. You've seen it enough time in the videos. Make sure you've got your copy on your revision notes for, just to remind you, we're on P10. So you have to have one piece of revision for P10. I am going to introduce a new term today, and it is called ohmic and non-ohmic resistors. So we're going to learn a little bit about the graphs that Ohm's law sort of follows, and we'll go from there. Okay, so here is a worksheet that I typically give out or put up on the board and get you to quickly draw it out as a table, and it's again just a great practice one, so when you come back to revising, you cover up your answers and just make sure you can do these. I'm going to demo the first one. I'm actually going to demo, I'll pick a couple out, and then I'll get you to pause, and then I'll put the answers up later on. So let's start up with total resistance. So I've got, so it's important that we know it's series circuit, 2 times 100, because we're just going to add them together. I should have done 100 plus 100, giving the same answer, 200 ohms. Okay, so that's our resistance. Okay, R equals. Now, in the next box, it's asking us what will the current be. So we've got V equals IR, but I want to find out what I is, so I need to rearrange that. So they're going to take R across the other side, so they're multiplied together over on the right hand side. So the opposite of multiply is divide. So I'll divide both sides, this side by R. That gets rid of my R on this side. But if I do it to one side, I've got to do it to the other. Okay, then I can cross these two out. So now I've got I equals V over R. Okay, so because I'm a bit tight on space, you've now got that in front of you, or I'll put it up the top just to make sure everyone, I equals voltage divided by resistance. Okay, so I'm going to drop those numbers in now. We've just worked out what the resistance was for this one, and it told us what voltage to use. That's good. So we've got a voltage of 12, and we're going to divide it by a resistance of 200. And if I get my calculator out and quickly put that in. Now, one thing when we're doing anything with electricity, guys, don't give your answers in fractions. Make sure you change them to decimals. So straight away my calculator gave me 3/50. That's no good. I want the decimals, and it came out as 0.06. Now it is in amps. Okay, so that's the first one done. Now that would be the same for, hang on, let's do it properly. Let's finish off that top line. So it's asking us now what the power is, and it's telling us which equation to use, and thankfully for us, we don't need to rearrange this one. So power equals current, which is I, times voltage, which is V. So our current, which we just worked out in the box next to it, 0.06, and our voltage is 12, which means our power is times 12, 25, 0.72, my calculator came out at 0.72, and it's in watts. Now, one thing I want to point out to you is look at my setting out. There's the equation. There's my substitution. There's my answer. The only thing that would be different, and it was a little bit different in this one, was there was a rearrangement as well. Okay, so nice and easy to follow. So that's the kind of format I want to see your answers in. Now, that will help you do the same for this one. Okay, so what I'll do is I'll demo this one now, parallel, just so you can see both, and then I'll let you get on and do the other ones. But again, you could just fast forward through the video, or you can actually practice. It's up to you. you know which one I'm going to tell you should do. Okay, so our parallel formula, total resistance, so 1 over our R for resistance, total, okay, equals 1 over R1 plus 1 over R2, okay, which equals, so that's my formula, all put in there. Now substitute the numbers in, 1 over 100 plus 1 over 100 equals 2 over 100. Now remember, at the end, I want to flip this. So I'm going to draw my little arrows in there just to make it clear. So 100, and I am running out of space, over 2 is now, well, I can simplify that further, and it would be 50 ohms. Okay, so I've got the same components. Two 100 ohm resistors and two 100 ohm resistors. The only difference here is one is in series and one is in parallel, but look at the difference. We've got 200 ohms here and 50 ohms here, so a lot lower. So that's the big difference between series and parallel circuits. I know I've said it a few times, but I just want to make sure we don't leave anyone behind there. Okay, so exactly the same principle. I don't think I need to do this box for you. You just use this number that you've just worked out instead of just substituting in. So rather than 200 ohms, you'll be putting 50 ohms in, and you'll get an answer for the current, and same for power. So the only difference between on this sheet is whether it's in series or parallel. And obviously, I've changed things up a little bit down top to bottom, and those are the ones I want you to do now. You can finish these two boxes off over here. I'm drawing little crosses on them so you know what I'm talking about. And then I want you to do all three of those. Hit pause, and then I will catch up with you. Now, if you would like a little stretch and challenge, okay, you might need to refer to your equation sheets here, or should I be kind? Ooh. Now, let's see if you can find it off the derived equation that we talked about earlier. There's my little hint for you. But it should be on your equation sheet, and that should help you solve it. And hit pause now, do all those, and then come back to me. Okay, so hopefully you pressed pause and didn't just scoot through that. You'll see, oh, hang on, we've got a different answer up there. That's different to what I put in, isn't it? I think I wrote 0.72. Let me just do a quick check. 100 times 12. 0.06 times 12. No, I definitely get 0.72. I think I probably borrowed this from somewhere else, which might mean some of these are also, these looks right, that looks right, that looks good. So there's some issues with the power. I wonder what I changed. So let's have a quick look. 0.24 times 12, and I got 2.88, so I agree with that one. 0.36 times 12, I get 4.32. Okay, so it looks like just the first one might have been wrong. And just to be 100% certain, 0.57 times 12 equals 6.84. Okay, right. So they look okay. Just this first one, which we did as a work example anyway. So hopefully the rest of them. If you do have any, of course, guys, that are wrong and I've made a mistake, you can earn some big brownie points by being nice, as you message me and emailing saying, "Sir, I think you've got one of them wrong." There are big brownie points available, and I won't do a shout out to embarrass you, but I will find a chocolate somewhere to reward you accordingly. So we'll move on to the next slide. Hopefully you've done that properly, and that is great practice. Like I said, come back to that again, cover it up, and just make sure you can remember which one's the series, which one's the parallel, how do I work out parallel. Obviously the parallel resistance is the big one, but once you've got that resistance, it's all the same. So the only thing you really need to do is be able to work out the total resistance by working out which type of circuit it is, and everything else is just the two other formulas that we've covered a couple of times. Okay, so guys, this is a retrieval activity. Now there is going to be a question straight off the bat. Now we're about 12 minutes into this video already, so if people are cheating and not watching the quiz, they're going to get caught out here, because the very first question I'm going to ask you on this week's quiz is, what were the retrieval activities out of? Now you'll notice there are 6 gaps. It is out of 6. Now, after that, I'm going to ask you what score you got. So what I'd like you to do is pause the video, see if you can fill in the 6 blanks. I'm going to show you the answers straight away, and I just want to know whether you are able to pull that information back out. And what I'll do to make this a little bit easier to start with, because it's a new activity that we're really pushing here. If you're going through all 6 and you get 3 or 4 of them, and after 30 seconds, that's it, you can't get any more, I want you to go and check your revision notes. If they're on your revision notes, fill them in, and then that way you're just going to get used to this repetition, this retrieval activity, so you're ready to go. So, pause the video, have a go at it, and I'll come back with the answers. Okay, so you'll notice that I've dropped in a 4th column there, but don't worry about that for the moment. This is our answers to the first one, so you'll need these for the equations later. And hopefully you knew the unit was the ampere, or amp I would have accepted, charge, joule, voltage, ohm, and the letter missing, symbol that we use in the equation for power, is a capital P. So, what mark did you get out of 6? Obviously don't show out the screen, I won't hear you, but I'm going to ask you in the quiz. As well as what was it out of? Well, there you go. I'm reminding you now. That's going to be question 1 in the quiz. It was out of 6. Now, your second retrieval activities, again, based on this box. Now, if it's not obvious by now how important this is, it's important. These are the equations that you must know. Now, the first one you're going to struggle with probably the most because we don't talk about it in a great bit of detail. The rest of them you can probably remember if you wrote down my little hints. How to remember the equation with Q in it. How to remember the ones with E in it, etc. So what I'll do is I'll get you to pause again. There are 6 to do. See if you can remember them, but after 30 seconds, if you completely stuck, get them off your revision notes, and I'll talk about them in about 5 seconds time. Okay, so hopefully you did pause the video and hopefully you're doing this properly, because otherwise this was a bit pointless and you won't learn. Because if you can't remember, not to quit on me, and that this is the equivalent. Okay, now equivalent comes up twice, this depends whether which one we're talking about, and our 2 big ones that are all our electricians across the land use, PIV and VER. And our derived equation for the stretch and challenge question previously was power equals I squared R. Now you could have put that together, it's just a combination of PIV and VER coming together, or you can just remember it, it's completely up to you. Now the first one was probably the trickiest because we only really talk about it in theory. So 1 amp in current is the equivalent of 1 volt, the potential difference of 1 volt with a resistance of 1 ohm. So the 1, 1 and 1. Now we haven't talked about that since the first slide, but here's a good chance for us to remember what it's all about. So 1 amp, 1 amp equals 1 volt over 1 ohm. So if you haven't written it down, quit. An equivalent, PIV and VER, and again, just make sure you've got that derived equation down the bottom. So what'd you get out of 6? I'll be curious to know. I'm going to ask you, you can either average it out, or you can, I won't ask them both separately, do an average. So if you got 5 and 5, brilliant, that makes it nice and easy. I won't give you a selection for 5.5, you can just use 5 for that one, and I won't hold it against you. Okay, a little bit of maths again, guys. So hit pause, have a crack at it, and I'm going to use this opportunity after about a 5-second pause just to go through it, show you how I would work it out, just to remind you, because we're going to do some more parallel circuits. And again, we need to make sure we can match denominators, add numerators, and come up with some solutions. So I'm going to pause the video and come back to you in about 5 seconds time. Okay, so hopefully you paused it. I'm back up on the screen here. So I have all these denominators, nice easy one to start with. They're all the same, which means I can just add the numerators together. 1, 2, 3. So I'm going to end up with 3 over 33. Now in parallel resistance, yes, we do flip these over, but because this is just the math side, we'll just leave them as they are. I need to also simplify this. I can divide top and bottom by 3, so I'd end up with 1 over 11. Both are correct, but this one is more correct. Now, our first trickier one here, we have 3 different denominators. So we need to, now, I very kindly picked 3 numbers that all fit into 48. So we're going to times 24 by 2, which means I need to times the top by 2 as well. 48 goes 6 times for number 8, which means I need to times the top by 6 as well. So I end up with 6 over 48 plus 2 over 48 plus 1 over 48, which means I've got 9 over 48. Does that simplify at all? Possibly. I'm going to cheat. Where's my calculator? Why not? There's no non-calculator physics exam, so if you're never sure, marketing calculator. Oh, it does simplify. 3, of course it does. I can divide it by 3. 3/16. There you go. And then obviously if it's parallel resistance, we'd be flipping it. But for now, let's just keep it nice and simple. Now the bottom one, if you haven't had a go at that one, sometimes people struggle. Now this is an example of it's not so easy to find a denominator to go into. Now I've got a little trick for this. You'll often find that however many times the smallest goes into the biggest, so it goes in 3 times there, you usually times the one in the middle by the same. Now that's not going to always work, but I find it often because of the kind of numbers they choose, it will work more times than not. So 660 times 3 is 1980. So to get to 1980 for this one, I need to times it by 6, and times top by 6, times that one by 3, times that by 3, times this one by 2, times by top by 2. So I'm going to end up with 61980 plus 31980 plus 21980, which gives me a sum total of 11 over 980. So if I take 1980, let's go 11 divided by 1980, put this calculator, oh, it simplifies down nicely to 1 over 180. So then if I was flipping that, I'd end up with 180 ohms. So these are examples of typical resistor values. So 330, 660s and 990s, they're typical resistance values, although that would just be 1000. And you'd end up with these 3 combined in parallel, you'd end up with a total resistance of 180 ohms. But of course, this was just showing you the maths behind it, and it's good practice. So well done if you got all those right. If you're not sure after seeing me go working through them, this is an opportunity now to roll back the video and have another go at them. And if you're still not sure, send me an email, say, sir, I've tried this, this and this, and it's not working. And we'll go from there. Oh, we're going to get answers now. Never mind. we go. Okay, so now I've worked it all through for you. You've seen the worked examples from the previous one. I want you to hit pause and we'll go from there. Just to remind you, once you do work out what 1 over 10 plus 1 over 20 plus 1 over 30 is, don't forget your last job is to flip it. It is a parallel circuit, so I'm going to flip them all three. Oh, and the only other thing that I always forget to tell people, and they always get very confused later on, is this is because we can't put decimal points on resistors. They're too small. So the K means 1,000. So this is actually 2,000. And then the next number is 200. So this one is 4,700 and 6,900. Okay, so fairly typical resistor values. There's nothing made up there. They're realistic as I can make them. So have a crack at them and see where you get to. Okay guys, so hopefully you've had a crack at them and the answers are up on the screen. All interest of transparency, I just sat here and worked them all out. So if there are any mistakes, please let me know. And you'll find there's a fairly simple trend there that you'll see that the resistance is reducing. So we're talking about, resistances of, about 1/3 in most cases. Now, if you'd like to know if you found this one quite tricky, don't worry too much. That's not unusual. Don't forget there's a lovely feature in your calculator, the fraction symbol, and you can put all of these in your calculator like this. Now, the only thing obviously you have to remember is whatever you get as an answer, you then need to put that into the next screen. Put the answer in there. You're flipping it in that instance, and you'll get an answer of about 1,231 ohms. And that's about all there is on that subject. So that's about as complicated as it gets. There is one little thing I'm going to throw right in the end, but next we're going to move on to Ohm's law. Okay, so there's a couple of notes that you need to take away from electricity, and it's this description called ohmic versus non-ohmic, which is should be fairly obvious. One is the complete opposite of the other. So we're going to deal with ohmic first because it's probably the easiest one, and I'm going to draw a couple of graphs. So I want to see these on your revision notes. That's quite important. Preferably use a ruler, please. I don't have that privilege in this instance. I'm drawing on the screen. And we're going to label these as our current, so capital I, and voltage. Now, as we increase voltage, current also increases. So, in a perfect world, we end up with this lovely line. And I'm trying to draw this as straight as possible. Now, obviously, when the voltage is 0, the current will be 0, but there's nothing to stop us saying we can have minus voltage and we can have minus current, but these will go in the same direction. There you go, that's about as good as I think I could draw that on the computer screen. So we've got I over V. Oh, where have we seen that before? So V equals IR, which is one of our equations of our equation sheet. Now if I rearrange this slightly, I'll move the I over to the other side, I'll end up with V divided by I equals R, which tells me that these two, V over I or I over V in this instance, that the gradient of this line is our resistance. And in this instance, it's not changing. The gradient, and I'll write that in just to make it really obvious, the gradient equals resistance. Gee, I wonder if this will be a question in the quiz. So the gradient equals resistance. Now, that's in a perfect system where the resistance never changes. Now, I won't hide the truth from you here. That's very unusual and a bit idealistic. LEDs are pretty good. So your LEDs in your TV screens and probably on your computer you're looking at, or your phone right now that you're looking at, they're not bad. They stay fairly constant. But what we generally find is as we increase our current in most items, our resistance starts to increase. Now, if our resistance starts to increase, it will start changing things. It will mean we need more voltage for the same amount of current, and it won't look like this nice, perfect straight line. So this ohmic means we have a straight line. Now, this will make a little bit more sense when we switch over to our non-ohmic. So I'm going to draw the same sort of graph. Now, examples, so I talked about LEDs being fairly close to being ohmic, and they're not bad. So an example of something that's very non-ohmic is anything that gets really hot when you heat it up. So the old filament light bulbs and the bulbs we use in experiments in class are a good example of this. And they might be ohmic for a really short period of time. So I'm going to draw a straight line in here. So you could say, actually, in this section here, our bulb is ohmic. Okay, fine. But what's going to start happening is, in order to get an increase in current... Okay, so sorry, I took a quick break there for 2 seconds. I'm just going to label these because I realised I didn't follow through with all doing. So as where were we up to? Oh, we're talking about what happens with a light bulb, for example. So as our light bulb increases in temperature, what we should have seen is this. What we actually start to see is this. And it goes up quite steeply. Now, we talked about the gradient or steepness before being the resistance. And if I draw resistance in here, it would be on this kind of slope. If I draw it in here, it would be on this kind of slope, and up here it's getting very steep. Okay, so my resistance is changing. So over in ohmic, our voltage is proportional to current. There is a relationship between them. And over here, there is not. No proportionality. I'll just no proportionate. Proportionality, I don't know how I can spell this. Proportionality to voltage and current. I should do an I for current. And now, just to not to confuse anybody, if you can go up in this direction, it also means you go down in this direction, and it will look something like that. Just to clarify, that's negative current, negative voltage. And all that just means is I've got the current flowing in the opposite direction as I'd had it before. So, some things you need to remember. Let's chuck these in. LEDs are fairly close to ohmic, but they don't have no negative currents. So they are only one direction. No negative currents. That's quite important. Bulbs, let's put light bulbs, bulbs, and lamps. Anything that is traditionally gets very hot, kettles. So your kettle to start with will the resistance will be quite low, and as it heats up, the resistance will go quite high quite quickly. Other examples of ohmic, thermistors. Now, we have talked about components before, thermistors. That's quite important because we want a thermistor to tell us for a given temperature, we want the resistance to change, so we can measure the resistance to work out the temperature back to front, if you like. And if my thermistor is on a non-ohmic curve, that's going to be really tricky to work out. So I want my thermistors to be close to ohmic. So the ones we use on the A-level course, which they're just about to start using actually, they're not bad. They're almost a straight line, but there's a few wobbles at either end. So guys, I'm just introducing you to ohmic and non-ohmic. Now that could be anything. You can make a stick, determine whether a stick is ohmic or non-ohmic. But traditionally we're going to be talking about LEDs and lamps and kettles, things that are more relevant to you. Okay, so I did tell you that there would be a little stretch and challenge at the end. Now, I will leave this for your choice. If you're finding this really easy, I want you to have a crack at this. I've given you some instructions there how to do it. If you're finding you're just coping with getting it done, that's fine. I won't be asking you any of these questions in the quiz. So there's going to be 10 quick questions in the quiz, and at least 8 of them will be easily achievable if you've watched this video through to the end. No problems whatsoever, but make sure you got notes, and make sure you use your notes when you're doing your quiz. I want to see some good first attempt results. However, if you get any wrong, please do have a second or third go at them. I don't want to discourage you from doing that. I just want to make sure your first go is a legitimate go. But well done for sticking it through the end, and we shall take it from there. Okay, so that's the end of the lesson, guys. So any questions, as per normal, please just email me through.